Hello and welcome to this video about matrices. In this video, we'll create functions to check if a matrix is orthogonal and then create random orthogonal matrices to test it. A matrix may be written out with row vectors in this notation, where v1 and v2 are lists of numbers and not just one number. The transpose of this matrix may be written out like this, with its vectors placed vertically, like this. If these matrices are square, then we can multiply them out like this. And we'll get a lot of dot products of these vectors, like this. If all of these vectors have a norm or magnitude of 1, then when they are dot producted together with themselves, then they will give 1. If they are all perpendicular to each other, then they will be dot producted together to make 0. Then we'll get this matrix, which is an identity matrix. We'll then say that this matrix is orthogonal if this equation is true. The transpose of this matrix can be written out like this, with row vectors, and is also orthogonal. If a matrix is orthogonal, then its transpose is equal to its inverse. So now to create a function that can test whether or not a matrix is orthogonal, we'll test matrix A, and get the transpose of A and put it into matrix B. Then we'll multiply them together to get matrix C. We'll round this matrix to get rid of all the inaccuracies due to numerical errors, so a number like 1 times 10 to the minus 10 will be rounded to 0. Then we'll test to see if this product matrix is the identity. If it is, then this Boolean variable will be set to true. Otherwise, it will be false. Then we'll return this Boolean variable so as to say whether or not the matrix is orthogonal. I've already defined these functions in my earlier videos. Now to test it, we'll create a function to make up random 3x3 orthogonal matrices. We'll start with the first row of this matrix. We'll use a random number generating function to get 3 numbers between minus 10 and 10 and place them into this first row vector. Then we'll normalize this vector so its magnitude will be 1, while its direction or ratio of all these numbers will be preserved. We'll firstly calculate the norm of this vector, which is the sum of the squares of all of its elements, and then this sum is square rooted. Then the normalized form of the vector is the vector divided by the magnitude of this vector. And then this is what this vector is after it has been normalized. I'm writing out these numbers to the accuracy of a calculator. This is all right because there's no real-world restrictions on how accurate these numbers can be. And then we can check this vector to see if its magnitude is equal to 1. Now to make the function to create a random 3x3 matrix. We'll set its size to be 3x3. The variable called PODP, which is short for part of the dot product, will contain a value that will be used to calculate the last element in the second row. We'll set the rows and columns of this matrix to be 3. So now we'll create the loop to put random numbers in each location of the first row. We'll also calculate the magnitude of this vector during this loop. Then we'll normalize this row vector here. Now to get the second row vector, we'll get only 2 random numbers this time and place these into the vector. We'll use the variable a here to stand for the last variable, and we'll use algebra to calculate it. So now to calculate the third variable, we'll start with this equation, which says that the first 2 row vectors must be perpendicular, so that their dot product will be 0. We'll substitute these vectors in. Then we'll expand the dot product. Then we'll use algebra to calculate A. And so this will be the second row vector, but we still have to normalize it. We'll create a loop to go through the first 2 elements of the second row and put random numbers into them. We'll partly calculate the magnitude of this vector. And we'll calculate this other variable so as to use it to get the third entry in the second row. So now to the next page of code. Here is where we'll calculate the third element in the second row, using the algebra that we've derived earlier. We'll calculate the magnitude of the second row vector here, and then use it to normalize this vector. And then to find the third vector, we need only use the cross product, which guarantees us that the third vector has a magnitude of 1 and is perpendicular to the first and second row vectors, and so we have a random 3x3 orthogonal matrix. Now to write code to make a random n by n orthogonal matrix. We'll firstly develop the theory here. So for the first row, we'll fill the row with random numbers. We'll write them in red when they are found as random numbers. So here's an example of random numbers placed into the first row of the matrix, which is the row vector v1. Then we'll calculate the norm or magnitude of this vector using this formula. We'll substitute all of the numbers into this formula, which will give us this number to a lot of significant figures. It's best to use a high degree of accuracy, since this is pure math, where it's at our advantage to do so. Then we'll normalize this row vector using this formula. We'll substitute all of the numbers into this formula, which will give us this normalized vector. I want to use color coding to show which stage these variables are at and where they came from. If I use blue and a tilde above the variable, then it means it is the unnormalized raw vector that has been calculated and that needs to be normalized. If the variable is red, then it means that it is a real number found using the random number function. If the variable is green, then it's a variable that has yet to be calculated using all of the previous row vectors and the recently found random numbers for this row vector. A black variable stands for an entry in a normalized row vector. A black bold-faced variable stands for a normalized row vector, ready to go into the matrix. So now to look at the construction of the first row again, using color coding. We'll firstly construct the raw unnormalized row vector by completely filling it with random numbers. Then we'll calculate the norm of this vector. Then we'll normalize this vector by using this formula. We'll divide every entry by the norm of this vector, and this is the value of each entry in this vector. So this will be the first row vector that has been normalized and ready to go into the matrix that we're constructing. Now to create the function to construct a random n by n orthogonal matrix. We'll pass the size of this matrix to this function through the parameter n and set the number of rows and columns to n. We'll place this matrix into B and set every element in B equal to 0. We'll create a loop to create every row of this matrix one row at a time. I is the row number. We'll create a loop to set the first n minus I elements in the row equal to a random number. Each time we increase the row number, there'll be one less element that we'll find in each row. We'll also measure the magnitude of each row with the information that we have, because we are still missing some elements in most of the rows. So now to get the second row of this matrix, I'm using the nth letter of the alphabet to represent the nth row, because all of the indices are beginning to get too messy. So we'll get all of the entries of this vector as random numbers, except for the last entry that we'll have to calculate. Since this row vector is perpendicular to the first row vector, then their dot product will be 0. We can then expand out this dot product in terms of all of the entries. We'll manipulate this equation to make the last entry of the second row vector to be the subject of it, thus giving us this entry. We can then normalize this vector using the following formula. These are the values of all of these entries. And so this is the final value of the second row of this matrix that we're creating. We can get the last element in the second row given by I is equal to 1 as a special case. We'll get part of the dot product all the way to the second last element of rows 1 and 2 and place it into L. We'll then divide it by the last element of row 1 and multiply it by -1 to get the last element of row 2. Now to calculate the third row of this matrix. We'll get random numbers to fill all of the entries of this vector, except for the last 2 entries, which we'll have to calculate from all of the last entries. And we'll use these 2 dot product equations to find these last 2 entries. We'll expand out these dot products. We'll manipulate these 2 equations so that the 2 variables that we wish to calculate and that are in green are on one side, and the rest of the variables are on the other side. Then we'll pack these 2 equations up into this one matrix equation and solve it to find these 2 variables. It's enough to show this equation, since we can send it to a matrix solving function to get the value of these variables. So now we have the completed form of this row vector. We'll normalize it using this formula. And so this is what these entries look like in this normalized vector, and we'll insert it into the matrix that we're constructing. Now to get the fourth row, we'll insert random values into all of the entries of this row vector except for the last 3 entries, which we'll use a 3x3 matrix to solve. This time this row vector is perpendicular to the first 3 row vectors, and so we get these 3 dot product equations. And then we'll expand these 3 dot product equations to give us these 3 equations. Then we'll manipulate these 3 equations so that all of the green entries yet to be found are on one side, and all of the red entries that we've already found are on the other side. I'll just create more space on the screen here. We'll pack these 3 equations up into this matrix equation and solve for these 3 green variables. So we have the unnormalized form of this matrix, and so we'll normalize it and place it into the matrix that we're constructing. And this is the matrix that we'll need to solve to find the last 4 entries of the 5th row of this matrix. I hope that you're starting to see a pattern emerging. Then, after having solved this matrix, we'll insert these values into the 5th row, and then normalize the 5th row. And this is the matrix that we'll have to solve to find the 6th row of this matrix. I'm putting more dots in this matrix to make it easier to see and get you used to seeing it in its more general form. And this is the matrix we'll have to solve to find the 7th row of this matrix. We'll define the ith and I-1th row and make these vectors stand for these rows, and using these entries from the Greek alphabet, so they don't stand for a particular row, since letters of the alphabet stand for the rows from 1 to 26. And so this is the matrix equation we'll have to solve to find the ith row of this matrix that we're constructing, and we'll have to write code that can construct this matrix equation for any value of I. So now when we get to the next rows after the 2nd row, we'll have to create a matrix to solve so as to find all of the elements of this row, since there are 2 or more elements left to find. This I is greater than 1 condition means it's for the next rows after the 2nd row, like the 3rd and 4th, etc. We'll make A into the matrix to solve so as to find the last I elements of the I plus 1th row. So we'll set the dimensions of A here, and it is an augmented matrix with the solutions in the last column. We'll make a loop to go through all of the rows of A and B. We'll fill up the main or coefficient part of matrix A with elements from matrix B. We'll get the location ready for the last column of this row. Then we'll calculate the element for this last column and insert it. We'll reduce matrix A, giving us the solutions to insert into the row from the last column of A. These solutions will correspond to the green variables that we described earlier. Then we'll insert these solutions into the matrix B, which is the orthogonal matrix that we're trying to make, but we still need to normalize this particular row vector. So then we'll get the magnitude of this row vector. Then we'll normalize it by dividing all of its elements by its magnitude, and so we'll get the row finished and ready to go through the loop to do the next row, until all of the rows are done. Now for a faster function to check if a matrix is orthogonal. It won't call any other function, and everything is done in the same loops. The matrix must be square, otherwise we'll return false. We'll set the variable n equal to the number of rows and columns to increase speed, and we'll set the return boolean variable equal to true until we can find a condition to turn it false. We'll create a loop to get the dot product of every row and every row underneath it. We'll round this dot product to get rid of tiny numerical errors. And if the dot product isn't 0, then these two rows aren't perpendicular, and therefore we'll set the boolean return variable to false and jump out of this loop and not enter the next loop. And we'll make a loop to get the dot product of every row with itself. This quantity must be 1 because the magnitude must be 1, and if it isn't, we'll set the return variable to 0 or false like before. Then return this variable saying whether or not this matrix is orthogonal. And this is what this matrix looks like. It's a transformation of unit vectors into other unit vectors that are perpendicular to each other, but are rotated and reflected so that distances and angles are preserved. So I hope that you have enjoyed this video and have found it helpful. If you have, please click like and subscribe. Feel free to share this video. Please leave some helpful thoughts in the comments. And thanks a lot for watching.